Okay. Hello, YT. Okay, yeah. So today's lecture will be mainly on computer thinking. So basically, we will discuss how to like come up with the solutions or like how you like how thought process go on when you solving the problem. So let's just first take the first problem, which will be interesting. And today's problem will be like bit of hard or something. So like yeah, hard means interest. Okay, any one of you have seen this problem before? Okay, yeah, yeah.
Is it ASL?
Yeah, you can guess from like okay, yeah, it is ASL from 2020.
Yeah. I see.
Okay. Okay, I will give you I guess some buffer problems there. Yeah, so if anyone has seen those questions before only, they can try the buffer problems. Wait, let me take a screenshot. Yeah. Okay. Have you done this one?
No.
Yes or no?
So which one are we supposed to try?
No, this is for like a buffer problem. So like if you have like if you have seen this problem we are taking, then just try this one. So like okay, you can try this. Like everyone just can take a screenshot. They can try now or like later. Uh, we will go with what we have. So yeah. So basically, we will start with this problem first. So let me explain the like what it say. So you given some sequence of number, and the only numbers we have are like plus one, minus one. So we can have some sequence like this, and there are like 2022 numbers, which like tell us this is like some problem from 2022 contest, but that's not point. Okay. Then oh yeah, so each number is either plus or minus one. Now okay, now what we have this okay, this is like a1 and so on. We select some indices. So basically what it's telling, like suppose you select this number, then either you can select this number or this number next. You cannot select more than like distance of two. So you cannot select some number have distance more than two. So suppose from here you select this number. Now you have to select either this number or this number. Suppose you select this number, then we again have same conditions. And likewise, we choose the number. Now this first number can be like any like in like we can start from here and we can select like each time some two gaps or something. So likewise, we choose this number. So like we choose the indices. So like any k and difference between indices should be like less than equal to two. And what we want to find is like suppose okay, suppose we have some sequence, this now what we will like we can choose this, then this, and yeah. No, okay, we will like starting the problems. We will start with this problem. Yeah, nothing. Yeah. So we have this number. If we select this number, so what we have to do, we some add them. We get two. Oh, no, I see one. Okay, minus one plus one plus one. We take modulo, which is actually one, which get an equal to c. Now what we have to find is like some largest c. Yeah. So basically what we have some sequence of 1 minus 1 of like 2022 numbers. Then we select the numbers with like some, not everything, but some indices with difference too. So we can just select this or like not too far away, just one or two step away. And then we add all of them. And we have to find like some like lower bound for all the sums. And this sequence can be anything like this can be like all plus plus, all minus minus ones, or like minus plus minus plus, and so on.
We are allowed to choose K and TITK, right?
Yes, yeah, we are allowed to choose k and tip, and yeah, basically like you are allowed to choose indices and like indices of which numbers you are, and they should be like gap of one or two. So like first, like after reading, we like formal, like understand what is going on. Now, what is like what you can think, how you can proceed from here.
Small cases.
Yes. Yeah. So like okay, it seems like 22 is like bit of relay, like maybe it be using like it's even or it's divisible by 3. Can be anything. But right now we will start with some small cases. So suppose we start with, suppose any, like okay, suppose this is n. Okay. Yeah, can I change? So suppose you take n equal to 2. So you have just two numbers which can like minus or plus 1. Other case is similar, and plus 1 plus 1. Now you can choose like what can be the maximum sum. So for here, like max sum can be only sums can be 0 or like 1. 0 when you select both, 1 you will select like only this number or only this number. So the maximum C can be like 1 only, because it cannot go more than 1 for this sequence. Now for this sequence, it can go to like 2. Like you select both of numbers and you get 2. So, but yeah, so you want like 2 less than, like C is less than 2 equal to 2. But we are already C is less than equal to 1. So like this seems like lower bound. And yeah, so for n equal to C equal to 1 satisfied. Now suppose we start with n equal to 3, which is yeah, one of the main. So suppose you have three numbers. They are 1, 1, 1, 1 minus 1, 1, 1 minus 1 minus 1. So okay, we can ignore these conditions because like in this case we already getting 3, but in this case we can never get 3. So yeah, we just look at this. What can you select? So suppose you select this number and this number. You cannot get 3, but you can get 2 sum. So you get sum equal to 2 here. Now here you can select this number, this number. So you get sum equal to minus 2. So mod of S is greater than equal to 2. Okay. So what we get? So like C can be equal to 2, basically. So like for any combination of three sequences of plus minus 1, you can have C equal to 2. Now, do you have any like idea from this base conditions, like n equal to 2, n equal to
N
3?
equals C equals N minus 1.
What?
C equals N minus 1.
No. Okay, that's the point. This is like,
Ceiling
so
of n by 2.
okay, no. So point is like, see, we are moving like two step ahead, right? So like for n equal to 3, there are like not even more the case, like more cases to work on. So we should select some larger n. So like for some problems, rather than like choosing so small n, we have to choose some larger n's. So like even n equal to 4 is also small. Suppose you take n equal to 4, okay? And I can give you, okay, I can give you one sequence. Suppose this sequence. What can be the like maximum C?
2.
Yeah,
2.
2. Yes. So C equal to 2. Because you cannot get 3 ever, because like there is minus 1 minus 2 minus 1 and 2 plus 1. Now can you get largest C, right? Yeah, so 2 should be the minimum. And for every sequence, suppose like for any sequence like of 4 numbers, uh you okay, so main point was like consider these first 3 numbers. There will be at least two ones or like at least two minus ones. And like you can just select them and get C equal to 2. So for like any sequence like of 4 numbers, you can get C equal to 2. Now suppose we, okay, so now intuition telling us like the answer could be n by 2, right? So let's try for more cases. Let's try for n equal to 6.
Could it be like the ceiling function of n over 2?
Maybe. Okay, what about n equal to 6? Tell me the sequence. Or okay, I will choose because like you guys will tell like 1, 1, 1. I will. Okay. What can be the maximum? Yeah.
3.
Is it 3? How can you get 3? Can you really get 3 here?
That's what was the problem with the base cases, because we were ignoring the condition about leaving the numbers between them.
Yes, yeah.
And yeah, we'll have to do more big
Yeah,
cases.
more bit cases or like okay, like some problems have like so much effect on base cases. We will cover them also. But yeah, so sometimes what happen, you have to look at like more general view of the problem. Now, actually, yeah. So like you can try like n equal to 6 now. So like for 6, what can we like see?
C
Here
is
you
equal to
cannot.
2, I think. That's
Yeah, because
minimum,
like
maximum.
yeah. So suppose you cover this minus 2, like you select this and this, you have to select one of these. So like the minus 1 will cancel with some 1, and then you can select one more minus 1. So you get like s equal to 2. And you can do it like this also. If you select 1, then you have to select one of the minus 1, and then you can select this both ones. But at the end you get like mod of sum equal to 2. So yeah. So what can we do now? The one of the idea was like, hmm, what about like this sequence? Plus 1, minus 1, plus 1, minus 1,
Why don't we
plus.
use blocks of 3?
Yes, that's the one good idea. What about blocks of 3? Uh, do you think that will be the maximum construction?
Not necessarily. We could have blocks of two alternating with blocks of one, and then we can have two copies of that.
Wait, blocks of 2 with blocks of 1.
Such
Like
as
how?
1 minus 1 minus 1, 1 minus 1 minus 1.
Yes. Yeah, that's indeed the like main construction we have to do. So okay, right now I will tell okay. We will try for like what, why not n by 3. We'll try one more condition, small case, n equal to 8. So suppose consider like some n equal to 8 condition. I don't know, I'm writing like random. Are there 8 numbers? No. Okay, we remove this one. Now what can be the maximum? Yeah, I don't know, even I am finding. Oh, we can achieve 3, right?
Yeah, 3. I'm thinking like greedy algorithm sort of in this, because we can just choose whatever we feel like with make the
Yeah.
sum.
So yeah, so like while now you're solving, like suppose you find some answer C, what we have to do is like we have to find way to like say we can always get C or greater than equal to C in any sequence of 222, 1, like plus 1 minus 1, right? And we also have to find some sequence where this equality hold. So like C is actually the sum of the numbers,
I guess
right?
it could be.
So this
Sorry,
is go on, go on.
sorry, I guess it could be 1/4 of it.
Yes, one
Not
fourth of
really.
it, right. So, okay, so as a Bhairav told us, we consider this sequence 1 minus 1 minus 1 1, 1 minus 1 minus 1. So it's like this block of fours. And
Actually,
now, yeah,
sorry.
y-
Earlier, I was thinking of 1 minus 1 minus 1, 1 minus 1 minus 1, but then you can choose both minus ones and then skip over the 1.
yeah, okay. Wait, what was like 1
This
minus 1 minus
will work.
1?
This will work. So,
Yeah, this one. So yeah, for this, like, okay, to not go for like n by 3, we would like, if you try this condition for n equal to 8, what can be like C maximum here again? So like one of, if you choose any of this, like you will get either two, suppose you choose minus ones, like this minus one, this minus one, you have to choose some one, then these two minus ones, right? Yeah, so like maximum S you can get is like 2. So C is like less than equal to 2. So for even 8 we get C equal to 2. Now what can you do? You
Wait,
can
C is
repeat.
equal to 3, right?
Yeah.
Is equal to 3, right?
3 will be 3
Minus 1
because
minus 1, 1
4
minus 1
negative
minus
ones and plus 1 is 1.
Ah, okay. Wait. Then how c equal to 3s? In by 4. Wait. It is here. Okay.
Yes, in this case, this will give 3. But in general, I guess it will give n by 4 plus 1.
Huh. Yeah, right. Okay. So thing is like we have 2022, which is like 2 mod 4. So like at the end we will have some other numbers like what? Sorry, 1 and minus 1. And if you try to like go for this one, you will like have to destroy one of the one. I guess, yeah. For like this will be 10. Yes. Okay, so general idea is like you have to come up with the construction, which is like 1 minus 1 minus 1 1. Again 1 minus 1 minus 1 1. And now if you repeat this till like some, yeah, 505 times 1 minus 1 minus 1 1, we get total, yeah, and we left with this. Now if you now, yeah, now if you try to calculate, you will always have like, yeah, you can only get like 2006. So like suppose you select like, suppose you try for minus 1. So this minus 1, this minus 1. You have to remove minus 1, one of the minus 1, then you go for here. So like after like each this thing, we have actually what? 3. Or like 1 plus this index 2. Now here what we will have? 1 plus 2. Yeah. 1 plus 1 plus 2. If you go for like this block. Because you will select one of this and you will destroy one of this. Select one of this, destroy one of this. So you will get at most one of the minus ones, and here you can get two of the minus one. So 1 plus 1 plus 2. And similarly till here you will get some like 500, 4 plus 2. And now for like if you want to get this 2, you will like have to destroy one of the minus 1 and get this. Or like even if you left as this, you will get like 5006. Everyone understand why we get 5006?
But what's the proof that it's minimal?
Okay, yeah. What's the proof? Because like you cannot go less than this, right? Wait. No, we want maximum, right? Like C should be maximum.
But we're not allowed to choose the sequence.
Yeah. So now I'm saying like, okay, we have some sequence prove like C equal to 5006, right? And now we will prove like for any sequence, the 5000 C should be the answer. Like first we are like come up with like what actually like can be the solution. Because like you cannot like random, like you maybe guess how you go for it, but it's like random, right? Yes. Now suppose C actually is equal to 5006. Or this is actually n by 4, right? Because we make a block of course. Some ceiling or floor. Yeah, simple. Now what we have to prove? Now, as I told you, there's one more part, or like as someone mentioned, we have to prove like any sequence of plus minus 1 of like 2002 numbers. You have to prove you can consider some sequence which give us some more than equal to 5006. So suppose there's like A1, A2 till 2002, and you select some numbers like this, and the difference should be 2. And now how can you show this condition? So what, okay, so what can we proceed? Like, okay, we have plus 1 and minus 1. So like let's just assume first like we have like more numbers of plus 1 than minus 1, like more of plus ones than minus 1. So then we will have like at least, oh, what is this, 1011 plus ones, like at least can be the more.
We can
Yes.
just like group one minus one groups of 4.
Yeah, but like not each time, like sometimes you can have like some
No,
minus 1
but
minus
then
1.
like we'll get like in a 4 term, the maximum can either be like 1 or minus 1.
Maximum can be 1 or minus 1. Like how? Like if you selecting like suppose some of the numbers are coming one, and if you have in this block you have all the minus ones. Then if
No,
you
like
select,
we take two ones and two minus ones. Alternate like that.
we don't have like ones in every four block, right? We can have like all the block of minus one.
No, like if we prove that for a sequence we need at least those many, then it's that much we've done, right? So we give a minimal sequence.
Wait, I don't
Uh,
get you. Like
The minimum sequence is found. We need to prove that every sequence follows that minimum.
yeah,
Oh
right
yeah.
now we
I think
yeah
we
right now we proving like any sequence can have subsequence of like this one.
I think we should choose all the ones or minus ones which are like more, like let's say the number of ones are more, then we could
Yeah,
like choose all the ones,
yeah,
and we could like try to choose as little minus ones as possible, like
yes, yeah. That's the idea.
whatever we can
So
avoid.
what can we do? Like first of all, we assume like without loss of generality that the number of ones are greater, and so as they are at 222, we have at least these many ones. And now, what can be like general idea? So like we have to like choose as max as ones. So like we can choose all of the ones and as less as minus ones, right?
So
So
it's
how can we?
so I guess
Yeah.
we can do like cases. The first case and the second case where we can take the number of ones is equal, greater than the number of minus ones, and the second case is the number of minus ones is greater than the number of ones. So
Yes,
both those cases will be symmetric, and
yes, yes.
so in that case we'll get in more than 506. So the only case that's left is the number of ones is equal to the number of minus ones, and that case we can prove. I guess that works.
Like this is like same now. Like we have first we have to prove like for like if number of plus ones are greater and greater than equal to are like same thing. Like we can have 2011's like ones and 2011 minus one, or we can have greater plus ones. They will like symmetric cases, right? Because at last we are taking modulus. So suppose we have this.
Yes.
Now what we consider is like suppose like if you consider some plus one, then we denote by Ci, and if you consider like minus one, we denote by Bi. Okay, let's consider reverse fire. Okay, and so what we will have some like some sequence of this type like B1, yeah, B1, C1, B2. Like if we can have B2 then C2 or something like that, right? What question was this? Where is the question? This I guess I can tell the like source now. What is this? 2022 C1. So shortlist first question. Yes. Now yeah. So suppose we have this sequence. Now what we have to cover? Like we have to cover as max as B1s and as less as CIs, right? So and what will be one's number? So number of ones. And what like we know the number of ones are like the coordinate is greater than equal to this number 1011. Yeah. Now what about this? How can you minimize the CIs?
Guess we just jump over them.
Yes.
So
Good. Okay. So point is, suppose you are at here right now. Ignore the what number you are. So suppose if you have minus one here and plus one here, so you can just jump over here, right? And you can ignore this minus one.
But we are
So
skipping one minus one for every minus one we have to pick. Like if we need to pick a minus one, we can skip another minus.
yes, yeah, yeah, that's the main idea. So why this? Yeah. So now, like the idea is like if you have like two consecutive minus one, you can actually skip one minus. Like in each of these both cases, like if there are like plus one here, like we can jump on plus one only. So in the both of these cases, like I should write. So if you have plus one minus one, and suppose you have minus one minus one. So you can just jump over both of these cases. So you can just ignore the half of the minus one, Like you just don't care about them. So like the number of CIs we cover is actually like not greater than equal to or like less than, but yeah. So like number of like at least how many minus ones we have, which can be equal to 1011, right? And half of that. So like basically the number of BIs we covering and number of CIs we are covering. So number of BIs we are covering is at least this much. Number of CIs we are covering is we can cover like we have to cover at least this much. And if you consider this sum, this is actually what? Uh, yeah, wait. Yeah, this is like this by
I
2.
don't understand how number of BI is greater than or equal to 1011. Like the CI
BI.
parting.
Okay, no. So BI is like plus 1, right? And we will always consider BI. Like whenever plus 1 come, we consider it. Like we jump on.
Okay, I do understand now.
Yeah. And when you have CI, we can always keep one of the CI in between two of the CI. So we can always like consider half of them. And when you consider like number of ones and number of minus one, we can consider half of them, and this is equal to sum this, which is like if you consider ceiling function, this is like 5006. And that's like we have a construction for 5006. So everyone understand. So what was like takeaway from the question? So first of all, yeah, right idea was rather than looking at all the general view, we can actually try for smaller cases. Now, when you like start trying for smaller cases, you like shouldn't really fall like quickly. Like, oh, we got this n minus one or like not local actually. Like, okay, I don't remember exactly, but if you like do this like formally or like neat calculation for any n, you can get the answer is n plus 2 by 4. I hope so. Is it true for 8? 10 by 4. Yeah. Wait,
In
not ceiling.
in the last step, why did we take the ceiling instead of gent? Because we don't know if we would be able to remove all the like when we
Wait,
half
yeah,
the
we take ceiling, like take ceiling on. This is equal to like 0.5.5,
no,
right?
but what if we aren't able to remove 505 like 506 minus ones? What if you're only able to remove 505 minus ones? Don't-
No, okay. So like how many minus one we have? Like if you have like some
1011.
1010, right?
Yes, then
We
we
can
would be
always
able to
like
remove 505.
wait, what? You
Then would
understand?
we would be able to remove five of well,
Yeah,
by
we
two of
can remove
this.
this much. Yeah. Now suppose you have these main numbers.
So,
Here we can also wait. Yeah, here we can also remove 505 one numbers, right? Like that one number can be go anywhere. Like
oh yeah,
in
sorry. Yeah,
yeah,
yes, yes.
or like even like okay, the answer can be 505 or 506, but we already have construction for like 506, right? Here,
Yeah, yeah. Okay.
yeah. So that's why like the answer should yeah. And if you consider for general n, I read on like EOPS, the general n answer comes out to be n plus 2 by 4 ceiling function. Yeah. So like what? So like after like for like this two jump thing, you have to try like greater examples like 6 or like 8 or like even 10. 10 is actually a good example. You should try for 10. Yeah. And then the main one of the main key idea was come up with this construction. So the sequence of like plus one minus one plus one. Yeah. Wow, what is my handwriting? Yes. So if you consider these blocks, uh, like after come up with this construction, we find the like minimum value, and then you can just like try to think little bit globally, like what is like how like what if like some kind of greedy, like we can select all the ones and like then we can always skip minus one, right? Yes. Okay. Everyone understand the solution, right?
Yeah.
Yeah. Uh, okay. Hmm. No, we like for this sequence is like our like we made it right for like attending the maximum value. That's why we just like consider these sequences. They are like together, like we consider them as a block. And yeah, so like the point is like to write it formally, we have to actually use like B and C. Like we have to denote the number of ones and plus ones, right? Yeah. Yeah, and this was 2021 C. Okay, now next problem we will try. Which one we should try? Do you guys have any idea? Like similar sequence question or some
No,
different?
different.
Different. Okay. So we will go for like some imaginations. Oh wow, go for problem. Have anyone seen this one? Hope some less people. Oh, there are 19 people. So many. Yes. Okay. This is actually like kind of nice question. Like sometimes 3D questions they might you have to imagine things. Yes. I will explain the question. Oh, I have to draw these diagrams. I consider that part, but like I never try too much. So like what we have 2000 like right now we can consider any n, but actually 2022 is relative here. But yeah. So like for this we have some beam. Beam is like some this kind of structure. This I don't know what I'm drawing. Yeah. These are like some like you can consider this type also. In like 3 dimension. What are the other dimension? This. So yeah, these are like only 3 type of orientation of one in 3D world. I hope everyone living in like 3D world. No one is like 4D. Yeah. And inside a beam, now we will place them. They mention it, right? So like beam is like 1 by 1 by 2022 prism. And then several beam inside a cube. Okay, and now what they do? They use some smart trick, some crazy. So they actually like divide one of like all the faces by 22 by 22 square. And what they want to say is like the all of the beam faces. So like this 1, 2, 3, 4, 5, 6. Six of the faces should click like should touching either the side of the cube, this side, or one of the other beam. So like a greater example is my video camera. So suppose you have some this B and suppose you have some other B, then they want like either this should touch in here, this also, this, and the up part and down part should also touch. What can they touch? They can touch to like other beams or like surface of the cubes. Yeah. So they write like this. So 1 by 1 faces of each should be like lie on opposite corner of cube. And that's why only possible like suppose you fill this with like n, right? 1, 2, 3, and so there are like 2022 square beams, and there are only like 3 type of beams possible. So this type of only beams possible. Then no two beams have to be intersect each other. So like you cannot have some beam here and like beam here like intersect. Why are we calling like okay? And yeah, so each of the 4 faces should touch either the face of the cube, like something like this, or the interior of another beam. And what we have to find is smallest number of beams we can place inside the cube. Interior means like cube interior. Okay, we have to draw so many cubes today. Yeah, so suppose we have some this beam place, right? So this is like inside a cube. Now you have to place some other cube covering this face. You have to place some other cube covering this face, right? Then you can cover this face by this. Likewise. Then something like this and something. So everyone understand what I'm trying to say. Okay, sorry. Yeah. I will give you some time to understand. So like you have cube, you have beam, and you have to cover all of its faces. Now note like each line this beam length is like 2022. So like this one by one faces will be covered by like some edge of the cube only, like not edge, what is boundary? Yeah, boundary of the cube. The only thing we have to consider is this other four sides, long side. So can anyone like come up with some construction or something? Or what should we do? What are your first thoughts? Yeah, we can flip a cube. Like it's isomorphic. Like you can just consider this, or anything. So like if you consider like something work for like number of x wala cube, y, z cubes. Okay, we can define that also. So first of all, we consider this orthogric axis. I don't really know what is x and y, but okay. Suppose this is x-axis, this is y-axis, and this is z-axis, right? Now this cube, which like facing one by one at like up down, right? Something like this. Yeah, we will call this cube as z beam. Okay, yeah, z beam. Then this cube, which actually suppose this cube like facing at this direction. So this is like y along the y direction. We call it y beam, and we call this x beam. This is actually very bad. I should draw a nice line. Something like this.
If we have two instead, we can do it with just three.
If we have two, you mean like 2 by 2 by 2 cube?
Yes. So I think I might.
Okay, that's actually nice idea. Okay, we define what is x, y, z like beam. So it's easy to talk. So suppose we have 2 by 2 square. And why we consider 2 by 2? Because like we have some even, and 1 by 1 is not like no one trying 1 by 1. Yes. Yeah, this is 2 by 2. Now, what is your idea? Like, how can we fill this?
So then I think I might have some cubes about. So
Yes.
we have a two beam like this, and any of them are the same because it's just a 2 by 2 by 2 cube.
Okay.
So
Yeah.
then we attach another to it perpendicularly like this.
Okay, I guess I understand. So you mean suppose like drawing is so hard, but okay. You have some cube like this here. Then you have some cube like this here. Something like this.
Yes, sort of
And then
like
wait, yeah. I should draw this also. And we have some cube here. Yeah, and this works actually. Because if you see this downside covered by this violet cube, this side covered by this, and other two side covers by side of the cube. So it's something like this. Now, one of the best way to like visualize cube construction is like look at the view from like different angle. So suppose you like take at some view. So like suppose you have top view, some this view, so like front view and side view. Consider like left side. Okay, so what we are actually having? So we have some this part filled by cube and this two part filled by this cube. Then here we have this part filled by cube and this part filled by cube. And here what we have? This and this. Now I guess, yeah. Okay, we did not consider that and that set, but yeah, this is enough. So like from top we can consider, yeah, this cube here. This is like one z cube, this is like x cube, and this is y cube, and they are covering each other. So for n equal to 2, we get like 3 cubes are enough. Now, can you like maybe try for like larger case?
I think for n equal to 3, like it would be 4.
doesn't have to be covered up.
Wait, what? Wait a second.
Wait,
Yeah.
we have to do it like minimum or maximum, because maximum we can fit
Yeah,
4.
maximum we can fit actually like consider like all the squares of this. So maximum we can fit n square or like actual greater. Yeah, n square. Minimum we have to find minimum.
Minimum. Why can't we just put in 0?
Zero.
Why can't we put in 0?
Oh, okay. Positive. Yeah. Wow.
1.
No, we cannot put one. So okay. Suppose you consider one. Now I will like, see how to go. Suppose you have this bad cube. Like
Okay,
not.
so the
Suppose like
longest
yeah. Suppose you have this. Then who will cover this side?
All sides needs to be covered.
Yeah, all sides need to be covered by like some beam should be touching. So like
Uh,
for this cube, like upper side and this side are like not covered. So you can just feel by like this another. Also, you notice like suppose you have this y directional beam, then you cannot have any x dimensional beam anymore. So only
yes, yes.
thing, yeah, only thing more you can have is like some z or some y.
Okay, so you need to waste space as much as possible.
Yeah. Oh, wait. Wastes in some sense, but like the you need to like fulfill the conditions. And actually the thing is like we have to find like first step is like find like some nice way to construct this. Once you get an answer, then it just some like after you constructing you just have to some formalize some arguments and some counting stuff. Wait, it's always possible to save to cover it. Yeah, it's always possible to no, not entire cube. We don't want to fill entire cube. We just want to cover the one of the face. So like you can just cover like this. Oh wait, it's different color. You can just cover this cube space by this.
But we
You
need to
don't.
just cover 4 faces, right?
Yeah,
Because 2 faces are already covered by the cube. I mean the big
yeah, two
cube.
faces. Yes, yes. So like even if you have something like this, so like this cube is touching this, so this face is now fulfilled, and even the other cube's second face is fulfilled.
I have some idea about the question.
Yes, yes. Wow.
Like what we can do is like uh, we can put 1 into n cube like on x direction and y direction and z direction, and we will get a cube of n minus 1, and recursively like it would be like 3 into n minus 1 total beams of light.
Like,
Can you show the question
like
again?
for induction, we cannot show like covering all the things, right? Like, okay, no, induction doesn't work. Like, if you have n by n, like, how you will consider the boundaries of the cube? Like,
The construction we got for 3 cross 3, why don't we repeat it?
okay, yeah, that's the idea. Okay, this is for like n equal to
Can you
2.
show the question again?
Yeah, this for like okay, I will tell the source after solid coloring. Each of the three set represent I don't get your idea. Three coloring represent arrangement. I guess you mean like some three type of cubes, but yeah, I'm considering it. Yeah, yeah. Okay. Now, so okay, look at this construction. Can you like increase increase it more? So suppose you have 6 by 6. I don't even or like 4 by 4 actually. One thing like come with intuition, like I guess you can try for like 3 by 3. That like even odd cases like doesn't really make sense. Like even if you find solution for odd cases, it's like easy way to like go for like even to even. And at the end we have 2022 even number. So we will like try to think for like evens and only. There can be construction for odd and also. Oh, yeah, we have to consider the middle one block. Yeah, that will be little bit different. Yeah. Okay, so suppose you have 4 by 4. Suppose you fill this square. Okay. And now what was our other square? It goes like this. Wait, I will draw. Yeah.
Like,
for-
yeah, so you can just get here. You can just continue this entire thing. The thing we got for 2 plus 2.
Okay, but like how you mean by continue? Like,
So you get this. Now what you do is that you recurse it in front also, you recurse it in back also. Yeah, exactly this thing.
yeah. So now I guess you mean you go for this side.
Again, yeah, yes.
Yes. And now we also consider this one. But
Yeah.
now we don't have to consider at
Yes.
yeah, okay.
Okay.
Now the part is like we don't consider at this level, like bottom level. We consider above this second one. Okay, let me name the cube so everyone understand. Suppose this is like beam 1, this is beam 2, okay, and this is beam 3.
Mm.
So what we consider now to cover this beam to this side, like front side, we consider beam 4 also. And rather than considering at this stage, we will consider it here, the middle, so that it can cover this left side of beam 3
Yes.
and also the front side of beam 2.
Okay, like what I'm telling is that the bottom beam only one is required, and the
Yeah,
other.
bottom, like each stage, like from bottom you required only one, then you have this beam, then we will like repeat the bottom one, like y cube x y x y, and z
Yes.
we will go like in diagonal style.
Yep.
Do you
Yep.
guys understand?
Could you like explain it again?
Yeah, okay. I will actually like for explanation I will like just finish the like construction and like, but yeah, okay, I want to prove actually how you come up with the construction. So first you try for 2 by 2, then what we actually do is I will like finish the construction. Is it okay. Yeah, yeah, this is better. Okay, so what we are doing, so we first place this cube. Okay, then we consider this cube. Okay, in our side we consider this side, but if you just like flip it in other direction, or like this is like symmetric xy. So you have this which covering the like left side of first one. So we get this second one, and we have this third one. This covering upper side of second and the front side of first one. Now we have to cover upper side of this third one, and also the like this left side, front side. So we place them like in the between. If you see this, wait, what is best way? Yeah, these are the red ones. So it's like in between here, and here we have that blue square, and here we have that green square, right? And we place the another red like Z in between. So like we just construct that front and front. So after we placing this, we will also place C, the cyan color here, the like or white
We
cube
can't
here.
draw, like we can't draw in the contest. I will write it.
Yeah, about drawing. So what is the best way to I told you best way to visualize this or like explain it is this. Okay, this is like one of the ways. So like uh, what we are doing, like from upside we considering this cube, from this right side. Right means yeah.
Wait, why is it skipping one square from the in the diagonal?
Okay, so like here we having this cube, right?
Right. Okay, got it.
Yeah. And the y level, z level is increasing at one time.
Yeah, okay, got it.
And see, like each time we have to use this and this for like each z levels. That's why we have like even ends. And so we will always consider all of the numbers.
Okay, now we have to prove it that it provides a
Yeah.
minimum.
Okay, so what we have actually, so for like from these are like 100, 1010 beams, right? Or like for even, sorry. So suppose n is the number, so these are n by 2 numbers, n by 2 and n by 2. So we get like 3n by 2 beams. Okay, first of all, I will like everyone understand why this construction works, right? And what is this construction actually? This is like the extension of like 2 by 2 thing we did. We just extend and we just like increase this size like x and y by 1 and like this. And then we also increase this as 1 and 1 like this. So everyone understand, first of all.
Yes, but like, do other constructions exist as well? Like, are we not
Okay,
missing
yeah.
out on
The
anything?
point is like there are like more construction of like same like you can get some more construction of 3n by 2 types. Like some other type of construction. Not flipping, like you can just flip a cube, that's not point, but some other type of things. Okay.
But we're not missing out on anything, right?
Huh. Okay, you can just check. So like for each this thing we covering one, right? Like we covering 3 of the things here. So we are always covering this left and right side of red beams. Then we are also covering this side, which is actually belongs.
Okay.
Yeah. And we don't need like Z wala things for like red one. Then you can do similar for here. So here you can, yeah, here like all the reds are like covered like this. You can see from like left side. Yeah. How you will now write the solution. So now I will like tell you how can you write. So first of all, you consider this coordinate system. What? This. So this is like 0, 0, 0. This is x direction. This is y direction. This is z direction. Okay, wait. You can like speak up. I have to read. Okay, yeah. Yes. Now let me tell you how can you write the construction, and then we will go like why this construction is minimum. Or we can do other actually this. You can see only one screen, right? The Miro. Hello.
Yes.
Yeah. Okay. I hope so. Yeah. Okay. So this is like the construction I like saw on like AOPS. So what they are actually telling is like this is like ZB. So if you see the like from up direction, we have this. Okay, this is like he denote this by 1, 1. So he's considering a little bit different by like up by one thing. But yeah, so this is like place at 1, 1, then 3, 3, 5, 5, and or like even this our construction. This is actually like 0, 0, and like the z direction can go from like 0 to n, right? Because we are considering the z beam, the perpendicular to z direction. And similarly, like 3 or 2, 2 star. So like see here, we have this z. Yeah, we have at like that corner. It's placed at like this. Yeah, 0, 0. You can denote by 1 over here. And then 3, 3, 2, 2, 4, 4, and so on. Now, similarly, you can construct for like other things also. Like this is like can denoted by some 2, 1 and 1, 2, and so on. So yeah, the writing the construction is the hard part, and this is like also not like okay. This is a more level question, maybe like hard in me, but yeah. If you come up with a solution, the best way is like just write this thing, and then we are like however way you write they just understand basically. But yeah, you have to write formally. Now what we will prove is for like n comma n is like even the minimum number of beams we need are 3n by 2. So what is the idea here? So first of all, like
Is this the reason why odd n fails?
okay, audience not actually fails, but like it's a different type of construction actually, which is like harder and like not needed at all, right? That's why. And okay, so when we like observing, our first observation was like we can do by n square way, right? So we will go with that. So suppose we have now we find like look for like local observation. So if you have some zero, wait, yeah, suppose the number of beams we have of this type, the perpendicular to z direction is equal to 0. So like we have no this type of beam. So every upper face or down face of every beam should cover by any of some y or x type of beam, right?
The one thing you observe that what's the value of okay no that's okay.
Okay. So what? No, we actually we round it. Wait, what is smallest number? We round it up. Like any of this construction should need at least 3n by like the beam number of beam construction should be like less than equal to or greater than equal to 3n. Right. Oh my god. Yes. Yeah. Okay. So what I want to say first of all, if there is some beam missing of like one orientation, so suppose we consider Z orientation and we don't have this type of beam. So we or everything covered by like X or Y. And suppose we have some Y like Y top of beam. So everything just can cover by Y now because you cannot use X here. And similarly for like each of the n layer of this cube. So we have to use n square beams. But like n square is greater than equal to like 3n by 2. Like we have n equal to 2022. This is true. So we consider we have at least one type of beam of like z, x, and y orientation. So like at least one type of beam of like all of this type z, x, y. Okay. Now what? Now we like look at like we have some kind of intuition, right? That each of the like beam require like some two beams, and like that's how we constructing UMOS. Like each beam, then we get two beams, then we have another beam, then we get two beams, another like upside down beam. Yeah. So first of all, like suppose we have some beam and we orient a cube so that it's become like Z beam. So suppose we have this square. Yes. And suppose we place a beam here. Okay, now we just look at this first floor or like, yeah, first layer Z equal to 1. What we needed, we need to cover how we formulate this argument. Okay, yeah. So each of this Z floor, right? We need at least one type of X or Y beam. That's our claim. So like for each layer in like Z direction, we need at least one XYB. So like suppose we have any like okay Z you can consider there like at least one Z, but now okay now here you cannot fit like X comma X or Y, so we have to consider some XY here, right? Then we need to cover the upper floor of that, like the upside of that, which can only cover by some another X or Y type of beam. Then up of that, like for each of the layers we have to need at least one type of X or Y beam. Did everyone understand?
Yes.
Yeah. So what I'm saying like for like, each theme you have to either like have to something up of that like from
So we
for
get
each of
plus
this.
y is greater than
Yeah.
equal to 2020, y plus z greater than equal to 2020, and z plus
Yes.
x.
Yes. So like for this like the X and Y type of beam. So okay, suppose like the type of beams in Z direction are NZ. For X it's NX and for Y it's NY. Notation others. Okay, fine. Then what we have is like xn plus ny, like nx plus ny is greater than equal to n. Or like for our case is like 2022. Yeah. So like because each time we need at least one, so like for n layer we need at least n of this. And we consider only z direction, and because we have one z beam, right? Now we will consider x direction. Then we at least need one of the y or z type of beam. We are double counting, but yeah, in like proper way. So like this sum should be greater than equal to n because like we have some X beam here, then we have to consider all of the like, how we consider, yeah, this type, this direction, I guess. No, we consider X, oh, this direction. So each of this direction have to like, okay, let me draw another diagram. What is M doing? Yeah. Here we consider Z direction. If you have something like this in X, so we have to something covering this floor, then something covering this floor, something covering this floor. So we at least need N type of such layers for like, which are like either Y or like X way, because sorry, Z way, because we cannot have X here. Or X is like this, yeah. So this is why we also have like ny plus nz greater than equal to n. And similarly, nz plus nx greater than equal to n. And if you add them up, we get like total number of beams should like greater than equal to 3n by 2. Did everyone understand? Because I did not explain that properly. It's hard to explain. Anyone like did not understand what is this like? How we get greater than
Can you
equal?
just show the first equation again?
Yeah, okay. So like each we have at least one Z type of beam, and for like each Z layer, we have to cover at least one of the layer with X or Y type of beams. So that's why Nx plus Ny is greater than equal to N.
But how do you know that there is a Z kind of beam?
Oh wait, what? How do you get?
How do you get that there is a Z beam? Because
No,
your
so no, what we are doing, like we are trying to bound the number of ways, like number of things. We don't have construction, but we are like bounding. So like this bounding is like low, like we don't know how we are constructing, but we know at least one will be exist in each layer. So we can say this bounding.
Right. And why is it greater than? I can get that. Not equal to.
Yeah, because like at like each layer we need at least one type of. We can have multiple, right? Like we can just have like all of the this covering by just X.
Oh, yeah, yeah.
We need at least one. That's why it's greater than.
How,
Yes.
how do you know that there has to be at least one too?
Yeah, because if there is not one tube, like sum of the direction equal to 0, then we have to cover all of them by like some n this type, right? And
Yes.
that will be n square. And n square is like larger than 3n by 2, right?
Yes, but
Hmm.
what about
No, so yeah, we consider like 3 dimensions. So like if like x equal to 0, like x direction or y direction equal to 0, the same thing works, just oriented the
no,
cube.
what I'm saying is like there could be some case that X equals to 0, but Y or Z not equals to 0. In that case, how do you proceed?
Yeah. No, like what I'm saying, suppose like some of the like x or y direction equal to 0, so we can orientate the cube so that we are just saying there's no upside down beam. So like z number of z beams are 0. Then when you don't have any like wait, yeah, when you don't have any of this type of cube, any of z direction, each of these layers have to be covered by x or y, right? Now suppose you have one x, then we cannot have y, so all of them has to cover by x. So we get like n cube beams in like first layer. Similarly, if you consider here y, then all of them have to cover by y. So like for each layer we get m beam, so we get n square beams only of
Okay,
like, yeah.
yeah, for each layer. Now do I understand?
Yeah, for each layer we at least need n because we don't have z direction beam available.
uh, actually I had a different question as well. So
Okay.
what if we have one Z beam and then in that plane there is
Hmm.
no other beam?
Wait, in then plane, like which plane? Like
In any plane, because you're saying in each layer there has to be at least one of the beams. So then
because
what
we have to cover like wait. front and left side of face of the Z beam, right?
Yes, you have it, but but you can't cover it by just covering it at one spot, right?
Yes. Yeah, but okay. So suppose you cover it by some X or Y beam, right? Then that X or Y beam have some upper layer which have to be covered. Suppose you cover by some another X Y beam. We cannot cover by Z because like we cannot have like less than 22. So then we again have upper layer. So each time we have some layers which is uncovered. And that's why we have to cover all of them by at least some X or Y.
Okay, I see. Thank you.
Yeah, yeah. Okay, now everyone understand. Like each is suppose you consider any X or Y beam, then we have to always cover the upper part of that. And that's why we always have to cover at least something in each layer. So we get at least n. And for like each direction, we do the same thing. And so we get the bound is at least n by 2, 3n by 2. Okay, everyone understand?
So it's harder
Like,
to find the constructions than like
yes.
do it.
Yeah, so what the construction come up with like the first thing, like 2 by 2.
It's like
Then
you get the intuition for the bound after you get the construction.
yeah, wait, did you ask or like you said?
No, I said here.
Okay. Yeah. So like okay. So first you like come up with like this 3 by 3, 2 by 2 is easy to imagine like what are we doing, and then you go for like some like try to imagine more or like to repeat these things. And once you like have some idea how can you do it, so like each this construction of 3D type of thing you have to like either try smaller cases or you have to somehow come up with the clever solution. So yeah, so we come up with this construction. Now the writing is actually hard part, but yeah, so this is one of the way to write. So like you can write like 1 comma 1 comma, so like we can just consider, or you can just consider this top left and right faces and then tell them like okay, this 1 comma 1 is covered, 3 comma 3 cover, 5 comma 5 comma, then in this suppose this is 0 comma 0, then 1 comma 1, 3 comma 3, 5 comma, like this is basically what we are saying. And even if you like you want like better way to like okay, yeah, then like we once we have construction we have to bound the things. So like for bounding we look see at like locally like what is actually going on with like each of the section. And once you like try to do that we get like that's like obvious intuition, right? Like if you have any beam then we have to cover upside, and then like we have to do all of the three sides. That's why we like at least need 3n by 2. So this will come up with intuition, the bound. Formal way is little bit like formal, but like once you like find in the intuition, you can write it up. So the source of this problem is where is it? US AMO 2022 P2. So yeah, I will suggest like go over the like AOPS and like see how the people write the solution. And this is like actually the hard problem. So like the solution sometimes have like some construction right like rigorously written, or sometimes you don't need that rigorous. We will see now. I hope we have time. Oh my god, this is so bad. Okay. Everyone understand this question, right? First of all, let's everyone understand this question. Yeah, cool problem. Yes. Yeah. No, like this was actually good problem. Like when I was trying, I actually like come up with this construction because of like imagination. But yeah, but I did not come up with how to bound these things. So this is like come up with experience and like intuition.
So how did you write the solution to this?
Oh,
Or
okay.
is this the only way?
Wait, how do you write a solution? You mean, right?
No, for this problem, how did you write it? Or like this or some other way?
Okay, that's a good question. So first of all, like all of the like cubes problem I see, I like we have to draw like some of this cube, like consider this 6 by 6 cube. So I will actually try to draw these things. So like I always do like black, blue and black what pencil, and I will like just draw this 6 by 6 cube, which actually give the intuition to like grade us what are we actually saying. And once like only thing we have to convince is like what are we saying. So once they convince, yeah, this is the construction, then you can like try to formalize it. So like I will suppose this is like 0, 0, and then I actually try to this grid the thing. Then I will write like all of this base thing we will have Z wala beam. Then consider this layer like similarly the top and bottom. The only like sad part, like once you see the construction, you did not get intuition, like what are we actually saying. So the drawing the one of like fewer size example is necessary. And then this is just like writing. This is easy. Like you just say like for n z equal to 0, we have n square thing. And for this thing, we have to at least cover by 1 because you have to cover each of the one layer upside of this thing. And that's why we get these 3 equations. Right. Yeah, and yeah, you can just you can actually this is like the photos are from like Iwan Chen solution. So like the solution is inspired by Iwan Chen or like the USM team. I don't know, but yeah, you can check their solutions. There's an okay, yeah, and okay, there's fun like many fun fact about this. So you know this is like construction of three 3030, right? And some like the USM person, actually I should know the name. What is the name? Okay, I will find the name, but yeah, that guy proved like there's like if you have 3030 beams and you have to cover like this cube, there are like 2 into some 2022 factorial square ways to do this without considering isomerism. Like you can rotate this cube like some 6 or sometimes, but considering that also we have some this large number. Wait, let me test my information. Just give me 1 second. Yeah, that guy's name is like Walter Stromquist, and yeah, from USA team, like grading team. This is there are this many like 2 into 1010 factorial cube base to like have like 3030 beams and construct them in this cube. And I don't know how to do that. Like you can this left has exercise for you guys. Find this, how we find this number. Yeah. Okay. What is going on in chat? What is this remark? Yeah. And this is also a nice construction. Yeah, there is puzzles also. Okay, so if you see this construction, there's another way to intuit. So if you now consider this box, and if you like move the box rigorously, so all of the cubes are like attached to each other, right, in fixed position, and so they are like no way to like rotate. So like they cannot go to X Y direction, the upside down cube, or suppose some Z Y type beam, it cannot go like Z or
Right.
X direction.
Right,
Yeah.
right. Yes.
Yes, so that's like physics interpretation of that interpretation. Yeah, so this was actually a cool problem, man. Nice. So, okay, now what you guys? So there was actually one problem. The reason I took this class was now it's already 8, and I'm pretty sure it cannot be covered in like half an hour. It's like harder than this.
How did we cover 2 problems in 1 hour?
It's just 1 hour. I feel like it's less. Wait, we cover like 2 problems in like 1.5 hours. They actually took so much time.
That's too much
Yeah.
time.
Yeah, actually. Sorry. Oh my god. Now I have to decide what should I do. Okay, I can share the problem, but like the how many guys can stay till 9? Like just raise your hand or uh like are you guys can raise your hand. Okay. If they are like more than half of the people in current can straight in line, then we can take that. And it's a beautiful problem, like so beautiful. Like that is the problem. That's why I'm doing combi so much. So beautiful. Okay. Why there are exactly 8? I said 8, that's why like people just like, no.
9 down. 10.
Okay. Now it's fine. Okay, guys. We
11.
will expand. We are infinite. I hope meeting run till then. I don't know. Okay, guys, raise your hands down. We will do it. Okay. Yeah. Here we go. One of the most beautiful problems. I will share this. This other problems will be in piece set. And there is one. Yeah. No, I don't want this line. Why it's there? Yes. Okay. First of all, we ignore the like. Okay. Give me 1 second of break. I need to drink water. You guys also drink water. Okay. Drink water. Yeah, you can raise your hands down. Okay. So everyone, okay. So if you like read the question and like I don't think that I mean you can understand. Wait. Yes. We will expand our vision. Uh we will use some already known facts like there's dots in zeros. Yes. I need to use them. Yes. So what is this problem, first of all, telling us? So you have some grid. I hope I can draw properly. Yes. You have some grid. So what is the meaning of broken line? So consider this grid. Okay. Then you have some line, suppose like this, which go only up or right. Like, okay. Consider this line. Now what you consider is like the square attached to it. So like this is so bad. Yeah. So consider these squares. So like if you consider all of these squares, basically, and they call this, so all this set of square, I will draw first to like showcase. Okay, so now, yeah, so for this red line, we consider like for each of the point, the adjacent, like the at least squares, one vertex should connect to that. And this is the worm. So this yellow part is they calling it worm, whatever. Yeah. And now what we have to do is like the number of ways. So like suppose some number of ways to uh, dominoes this. So like dominoes are like 2 by 2 or 1 by 2 things, these dominoes, and we have to cover them with here. So first of all, let's like try example. For this, how can you cover, like give me like idea. How should I cover this one? Upside down.
Can
Wait.
you show us the question once more?
Okay, no, I will like you can read, but I will explain the question once again. So what we have, okay, I'm explaining from start. We have some line in like grid. So it should pass through integer point and it can only go up or right. Then we consider the squares adjacent to it. So like this, suppose this integer point, then the square adjacent to it are like this one, this one, this one, and this one. And we consider all of these squares. And they together form one structure, which is like, look like worm, right? So it's called a worm. This yellow, like not oil, orange color thing. Okay, okay, do not read the like. Later we will prove what we have to do. First we have to understand the process, right? So first we try to process what. So what we have to do is cover them with dominoes. Okay, so I explain what is domino. So let me explain what is. So suppose you have this. So you consider this domino, this. Now suppose you consider this domino. Can you just tell me what will be next only place we can do? Like see. Yeah. So like here only way to do is this. Now here if you want to cover this square, we have to place domino like this. To cover this, we have to place like this. Now we left with this area. So like again we can place something like this and like something like this. And now we can do here like anyway. Right. This is the one of the way.
I
Okay.
think we can consider the intersections like the turning points. Till then, we can count the number of ways by induction and then we can change them.
Okay. Yeah, we are on right track. So like thing is like okay, after this point, you can actually cover this by this way or like some of like this way. Okay. But so we are actually have so many options after like some point. And but the thing is the when you try more cases, now we will try some more cases before we come up with any argument. So suppose consider this pattern. Okay, or actually not this. Uh, yeah. Now, like you guys, so this is the worm. Uh, wow, very smooth. Okay, I hope this grid look like grid.
You missed this one.
Oh, okay. Wait, oh, I missed this one. Oh no, I basic.
No, you missed this one. I'm sorry. This one.
Yeah, okay, yes.
And
Now, oh, which one?
this one.
No, it should need it, right? Like this. Oh, okay. The yellow bar. Okay, fine. Yeah, yellow bar. Okay. Now we have this worm, like broken line, and we consider this worm. Now for this, come up with like thing. So suppose I place like this, one domino. Okay. Now what are the ways to cover? Can you see? Right.
It's you're forced for all the way down the staircase.
Yes. So we actually force. So like for this we have to do like this. For now for cover this square we have to consider horizontal. No, not vertical. For this we have again I have to like all this down we have to consider the
You
horizontal
just
way.
draw lines instead of drawing the dominoes themselves.
Yeah. But yeah. Then we left with this area which we can cover either this way or like some other this way.
So when the staircase is of equal length, till then the moves are forced.
Okay. That's a right idea. So what is mean like okay, what is mean by staircase first? This, right? Now suppose we have this thing. So now it's no more staircase. Like staircase is like from this area to this area. So the staircase always have equal number of moves. And now what you say, who is what? Taniksha, that T like for staircase way, we always have forced move. So okay, I will consider this. Now we will go little bit further. So suppose this example. Actually, we can consider this one. Is there any way to copy? Yes, magic. Save my time. Yes. Now suppose we remove this dominoes, which I draw
Now,
like
like if you fill that top grid, then also you have one way. Yes.
yeah. No, okay. So what we have actually. So suppose we fill this in this way first, like in first
Yeah,
time we
this
fill.
way. This way.
Yeah, no. So first time we fill like this, and now till this area. Wait. Yes. till this area we have like only
One
one way. Everything is forced. And then here we can do it by like two ways. Now, suppose we do not do this and we actually change in this way. So if you do like this, now what can we have?
Still
So if
one way.
not still one way, because
No,
now
two,
you
many
now you
ways.
can like
Many ways.
start with here like this and like now this will force, or you can actually start like this.
Yes. I
Yeah.
think.
Yes. Or like even you can do like this. Suppose you start here and then you go down and down.
Yeah, so
So
three ways.
or okay. So or what you can consider, suppose you did not consider this part. So you did not consider this index. Then what will be the worm actually? This part, right? You just not consider this vertex and the worm will be like all the things ignoring it, removing upper to bound. So, and what we have, so like if you place something this horizontal, right? If you place this horizontally, and if the number of ways to do for like this worm, like just this worm till here, is suppose some like suppose now it's like f of s, okay? And then what we did is like we extend this to here, and now the another this way is like f of some t. Then what we have like f of t is actually equal to when we place like some this block. Yeah, when we place this, we just have to cover f of s things. So it will be actually equal to f of s plus some other things. What are the other things? When you consider this case, when you like consider this upside down, now you cannot have f of s like same structure again. But now if you see this part, you are actually forced to like till some extent. Like you are forced to do this thing till this extent. Do you guys understand? Is some other part which is like maybe forced till like some end. Right? Okay, I will try one more example to like get the feel.
One idea could be like we can define a worm like if x comma y and and
Yeah.
see that like for if x plus 1 comma y or if x comma y plus 1 what the
Yes,
changes happen like that.
that is the idea. Yeah. So like yes, the idea is like okay, we will try another case to like get more of this field. Now we actually get some amount of intuition. Now we just have to like okay, why I'm doing this? Yeah. I will not draw like middle lines. Okay, I will actually draw. Makes sense.
So we have to define a different function for each staircase. And then
Yes,
when everything, the intersections are vertical, we have to consider those cases.
yes. So
And it
okay,
depends on the number of staircases.
yeah, number of staircase. So first of all, like staircase like this structure, so like upside, upside. Then once you end with staircase, then you like now from here we get go to right, and then we no more go to up. We go to like again right. Now here we end the staircase. So staircase goes till like this. I actually this or that. Okay, I'm calling this extra. Oh, okay. This is not part of the square. Okay. Yeah. How we are forced then. Yeah, we are, yeah. Now what we have, once you break down this into these two parts, then the number of ways to do this without staircase and number of ways to do this with staircase is different. And for each like staircase thing, yeah, suppose you do like this, wait, let me change the colors. I have to yeah. Suppose you color like this, or you can color like this also. Like there are four ways to do this. And now we remain with this structure, remaining structure. So suppose like the number of ways to do this, like f of t, then and remaining structure have f of s, like number of ways. Then f of t is equal to what? F of s plus, now we actually have to cover like let me remove this bars. Yeah, and then we actually have to cover this thing. Suppose we cover like this, and now other all things till like staircase end. So like this, you can, yeah, you have to do this. Did I make a mistake somewhere? Oh, we actually have to consider this square. Ah, I thought so. Why this is going on? Yeah, because it's connect to this part. Yeah, then we get this structure. I hope you guys following me. Yes. So now once you like cross the staircase, we only have like one way. So like the staircase is some fixed thing, right? Yes. Yeah. Now, if you try for small example, each staircase is fixed. Now, and suppose you like go like some finite amount. So suppose like we consider back. This is like same condition. So suppose you go till here without staircase, then this is just like some standard way to count, right? The where this staircase is. Yeah. So number of ways to do this, then this staircase, and then we have this thing. Each thing count differently. So like if you do staircase one force way, and you can do this like that many times and this that many times. Or like if you start with this is f of z, then we get some this all thing is f of s. F of s is equal to f of z plus some case where we like mix with staircase. Then we just consider this part and the other staircase. So other thing. Then f of s t will come off to be f of s plus t. So this is like some kind of recurrence. And only thing we distinguish is like staircase and the continuous block.
So the
Right?
staircase part is forced.
Yes. Yeah. So yeah. Okay. This is nice way to say that. So
Wait, I lost you there. What is f of z or s? Like,
okay. F of z is like number of ways to cover this part of the
like the
worm.
straight part.
Yeah. And f of s is like number of ways to cover beyond this green line. I will change the color. Beyond this cyan line.
Oh.
Can
And
you
all of,
consider the case when we have like two staircases of different lengths?
okay,
Like one is
no,
like
so
one block
like
away and
the,
two blocks.
yes. Yeah, so we will like suppose we have another like staircase or something here. But yeah, the length of staircase is like not like matter in that way. But okay, what we actually saying now, let me say properly that the total number of ways f of t, then f of t is either equal to like color this box and then consider this part, which is f of s, or it's equal to you force things up and then you force till some extent when staircase end, right? So this is like something like something till like we are, and like for this argument like we are forced for like staircase. Okay, so did you guys got intuition? So each of the worm we either fix like we fill the first part and we consider other part, or we add like, or we do the forced staircase. So what we are going to do now, we are actually like recursively define what is like the number of ways. And okay, so okay,
I've got a question. Like in
yes.
this case, it's like a continuous staircase. Like what if they're like broken staircases? Like we have f of z's
Yeah.
between the staircase. Then you have to
Okay.
break it down, right?
Yes. Wait. I will explain. So suppose, okay, just let me remove this. So what we actually doing is like Okay, now suppose we have another. So we also extend till here. We extend here. And now this is no more like this is staircase till here. Because like this zigzag, zigzag, zigzag. And then we have like this other part. Just let me draw once. Give me a second. Yes. Okay. Now what we are actually telling. Suppose the total number of ways to like dominoes or like tile this wall is f of t. Okay. Now what is f of t? F of t either equals to this. Suppose you color this thing and then you left with this tile. So like once you color like this first domino, whatever else remains is like f of s. So like number of ways to tile this only this remaining dominoes is f of s, right? Which is you can actually get like just continue your broken line till here. So f of t equal to f of s plus what? Plus if you consider this dominoes. So suppose you dominoes like this, then you have to like force all the staircases till this line. And now what we left with? So now you consider this part. So like here you can have anything. Like I'm saying like anything. Like you can have some other staircase. Okay, we can go to the left, right? But yeah, anything like beyond this line, we will consider it as f of z. Okay. So what is f of s beyond this first domino? And what is f of z beyond this staircase? Like once you end with one staircase, then what is f of t actually is f of s plus f of z. Because when you apply f of like this domino, we force till z, and then z can be anything. Now you guys understand?
Okay.
Yes. And okay, and the thing matters like suppose you are like extending here, then we just consider this first case, and above other are like f of s. So this will be like same thing, and this other will be like f of like s minus 2.
But if
Oh,
the like worm does like two right side, then one up, like there
yes.
is no step.
Yeah. So what are we actually like in some forms recurrencing is like either you consider horizontal, vertical type, for which we get f of s, or you consider one horizontal. And when you consider horizontal, we force. And not in each case. Some case we will not force where we don't have staircase, but then we will have like beyond then we will have staircase. So the other numbers we will recurrence the things. Okay. Now we will start the like this is the main idea. So like once you got the main feel of the problem, so what we are actually doing is either we continue like my uh, you know the Fibonacci wala thing. So the idea is come up from this. So you know the number of ways to like dominoes this n by one thing. Either you what you do, either you do for like this n minus one, or you do for n minus two. We are doing same thing, but now because of the staircase case, we actually once we have some force thing, we actually end up with like some here. And now we will okay. That's the intuition whole problem. So everyone understand what is like process, what is going on. And now we will try to like formalize this thing.
Now we just have to find the ways of like vertical. If we
Okay.
have a lot of things in staircase,
Yeah.
that's it, right?
Like way to find the like recurrence. Right. So, okay, now we will go back to the problem. So what problem actually saying? Prove that number of ways to worm. So like number of worms like this, they can divide into dominoes in exactly n ways. So like this number of worms divide in exactly n ways is phi of n. Phi of n is like number of numbers less than n co-prime to n. I hope everyone know like suppose like we have phi of 6. So how many numbers less than 6 co-prime to 6? 1, 5, and yeah, 5, 2. So f of 6 is 2. So what is telling is like number of ways number of worms which can only cover in 6 ways are 2. There are only 2 worms which can cover in 6 ways. There cannot be more or less. Okay. Now this seems so like what is going on, but we actually go a bit of like in this. So well, now we have intuition what is going on. So now we will start from like base cases. Okay. Everyone understand till here, right? What is the
Yeah.
time? Okay. Yeah, we are covering fast. Uh, yeah. Now we will start with some magic. So suppose we consider like what do you call yeah, we'll start with index. So suppose we have some worm, okay, which is at this position. And now we count number of ways. So like the length of worm is 0. So suppose this is like omega 0. If it's go to left, right, we will go to right. If it's go to up, we will go to left. Okay. So like if you have some like something like this. Okay, what are we actually going? We're going like right, up, right, up, right, and then again right. Okay, and what are actually these vertices? We will denote the number of ways to like fill up this worm with dominoes, and then we will actually like do how we will find that out. Okay, so everyone understand how this like this is called like binary tree. So how this binary tree defined? So each of the vertex have two degree which go like down like this, right? And what we doing, we go to like right if we are going to like right in the original worm, and if the worm going up, then we will go to left side. Okay, now what for first in this? So suppose we have just dot. So how many ways to dominoes this? Like how many ways you can domino this? Yeah, this is same as segment tree, but segment tree is like sum of the numbers. We are counting the number of ways. Okay, guys, we will start with it. So, how many ways to dominoes this one square? Like this, the dot, the domino is just dot, then square 2, right? So we will write 2 here. So there are 2 ways. Now, suppose we go like, okay, the cases are symmetric over like one say, like you can assume it's going up or it's going down, which is like same thing. So we just consider this side. So suppose it go right side, then what we are left with? We have this thing, right? Now, how many ways you can like dominoes this one length worm?
3 ways.
3 ways, because like this one and like you can actually yeah 2 and actually this and this. So there are like 3 ways to do it. So once you go to right, you get like 3 ways to do. And if you like consider like suppose some vertex here which name like 1, then what are we actually doing is like 1 plus 2 is 3. Okay, we will continue what are we actually trying to achieve. Now suppose we have something dominoes of this length, then this is just increasing, right? So it will be like previous number and sum of previous number, right?
Yeah.
So 3 by 2 and 2
5.
by 2. So 2 by 2 we have 2 and 3 by 2 we have 3. So this will be like 2 plus 3 equal to 5. Yes. And again, if you again go like left side, this is like going a similar way of Fibonacci series, right? So again, we have like sum of last 2 numbers. And so we will have this equal to 8. 5 plus, okay, 3 plus 5 equal to 8. Now, suppose rather than like just after moving once up, like right side, suppose you move up. So now what we have? We have this structure, right? Yeah. Now, how many ways you can do this structure? So one of the ways is to like fill this gap. Now you left with 3 by 2 or like just this thing. So this number of ways will be 3 plus suppose you do like horizontal. Then you are forced to do this, forced to do this, forced to do this. So you are forced in all way. You understand? You are actually forced in all way. So, and what are we actually doing? So follow the staircase, right? So what is this staircase going? So you actually go like, here we are going like up, and here we are moving right. So we are like, from this index we moving right and up, and this is only the length of staircase, and we consider this number above this, and like at the like left side above, which is 1. This is like default, we consider it like. And so what I am saying is like, suppose now we consider this number. Okay, what is this actually? We telling like, we have this index, then we go once right, we go twice right, and we go up. Okay, and what is the number of ways to dominoes this thing? Yeah, it's like either you dominoes it in like this way. If you place domino here, it will be become like 3 by 2, or like this thing 5, right? So it will be 5, plus if you dominoes like this will cover, this will cover, and you just left with this thing. And what is this thing? This is like 2 by 2, which is this. So what are we actually doing? We go for staircase. So this staircase end here. So we consider the previous number 2. So 2 plus previous number 5. It will be 7. So do
So
you
that's
guys
why we put
understand?
1 also in the previous one, because there was a
No,
staircase of
because
3
like
plus 1.
we are following staircase. So like once you get left, you go right. If you go like left, then we have to consider previous number. But if you're not going right, like left now, so we end with here, and then we consider only previous number.
No, I was saying in the 3 plus 1 equal to 4, the one we got is because of the staircase which we took. So, and the previous vertex was 1.
Yeah. This is like assume, because like to this tree work, the number be previous to 2 is 1.
Okay.
Yeah. So everyone understand. So each point in this vertex denotes some worm, and we actually this word tree covers all the worms, because in each worm you either go to left or right. Sorry, right or up. And each of the way to calculate, if you have staircase, then we just consider like all the stair. Okay. So yeah. So if you have this type of thing, and suppose this is A and B, then we consider A plus B, right? Because like this, anything happening, this is our worm, this is previous B worm, and this is previous A worm. Yeah, and now this part will be this worm. This part is just this worm. Like the worm beside this we ignore actually. Like this will be some another tree construction, and this worm is just still here. So we consider A plus B. And suppose we have something like this. So what is actually doing is telling us there's some kind of tree structure, and then we have again this. So like some staircase, and we have this one. So if this is like yeah, this is suppose A, and this is B, then this will be A plus B, and this is like some staircase follow, and this number will be this previous number. Suppose this is C plus we follow all the staircase, because this staircase will be forced in like tiling in the wall, and this will follow till B, and that's why we consider A. So this number will be C plus A.
It's like each branch is like
Yes.
the two directions, right? One going up, other going right.
Yes. And like in our branch thing, it's like if you are going up, then we're going left. And if we are going right, then we're going right in the branch. So we convert all of the ones thing into branch thing.
Can
And
you
now,
explain the part like where the C plus A come from?
okay, yeah. So the thing is like, suppose you have this, right? This is the worm denoting at this point. Okay. Then this worm is either just consider this horizontal tile and consider all the remaining worm, which is actually C. Right.
Yeah.
And what is other way? So for C, this staircase telling us it's going like up, right, up, right, up, right, right, till here, D. So till here we get D, and this part beyond like B is like number of ways to do is actually A, right?
Yeah, okay, I do
Yeah.
understand.
And this staircase is forced. We seen from example, right? And that's why this staircase will be forced, and this number will be C plus continuing the staircase till A. So now can you see, like, now we just have to calculate this tree. So what, like, okay, can you guys calculate, like, help me to calculate more? So yeah, what can be this number? This number. This is like 4 and this number 3, right? Because we are going like up and up, and we don't have any staircase. So this number will be 7. And what is this number? This number will be 4 plus we follow the staircase. So we get here and here and yeah, and here. And now we stop for staircase because we no more have. So we will consider 1. So 4 plus 1, 5. Uh, okay, everyone understand. Now, okay, we don't have enough space. Wow, what a bad way. Okay, I will draw another thing. And now we will like try to calculate what actually we having. So this is like number of ways 2. Then we go here. This is 3. This is 5. And if you go here, what was this? This is like the staircase 1, 4. 1 plus 3, 4. 2 plus 3, 5. I'm writing because like maybe you guys like don't know some like how to add. That's why I'm writing. Not really. This is 4 plus 1. Okay, what is here? Like, can someone tell me what should be sum here? If you understand. So we
7,
consider yeah. So we
5 plus
consider
2.
previous
7.
number. Yeah, we consider previous number 5, and then we follow the staircase. So staircase go till here, and so the previous number is 2. So this will be 7. And what will be this number?
8.
8. Uh, 5 plus 3, 8. I should write in nice. Okay. Now we will extend this again because, and you guys have to tell me because I'm not going to calculate everything. So yeah, now tell me what will be here. Quick.
11.
Yeah, 11. Because we got like previous number is 7 and the staircase just end at 7. So previous number is 4. So this will be 11. 11. What will be here?
10, I think.
Yes. So 7, the previous number, and this staircase actually go till 4 because like this staircase, and so we consider 3. So this is 10. Now what will be here?
9 and
Wait,
the other one.
9 or
7.
6. So previous number is 5, that's sure. Now where the staircase going? This go here, here, then here, and this stops. So we
Oh, we
consider,
put that up. Okay, okay.
yeah, we not add, like we add the previous and the staircase. So we get this equal to 9. Wow. Then what about this?
Okay, it's 6, not 9.
Oh, 6, yeah. Yeah, 1 plus 5. Yeah, and this will be 9, right? Because you add 5 and 4 because we don't
Yeah,
have
yeah.
any more. Yeah. And now what will be this number?
12.
12. Yes, 7 plus 5, 12. What will be this number?
10.
No, not 10. 7 plus the staircase follow till 3. So we consider 2. 9. Here I will do quickly. What is this? 3 plus 8, 11, and this will be 30. Okay. Now everyone understanding like what is happening. Each of these vertex is some one, and we calculate sum because like either we go to previous or we go till like the staircase follow. Now observe, like try to observe. I know I like draw this badly, but yeah. So try to observe how each sum is going. Like, can you guys follow any property? Also, just to like, if anyone confused, we also have another node here. But if you consider like this, just reflection, like it's just like either you go up or down, right? Then the same thing we're doing here, we can do like here also. So we just consider like one of the part. There is same thing reflection and the sum will follow in same.
Is it
Uh,
is it
yeah.
the same?
Okay,
Is
okay.
it just
Wait,
everything
wait,
is
wait a second. Wait. Okay, I will say everyone understand, right? I hope like no one just confused too much. Anyone have any doubt? Like you don't understand anything? Like ask me. If you even don't understand what is one here or two here. Okay, if no one is responding, I assume everyone understand. Then now, okay, now try to observe what are the sums. Like what can you follow from here? And also remember, we want to find like the n. So like how number of time n come in this tree. And what will be that tree? It will be some sum of two numbers, a plus b. Okay, yeah. Now go on. We also, yeah, and we have to find like this should be phi of n. Phi is like coprime.
yes.
That's
So is it just all the times where the two elements, the two numbers summing to it are co-prime? Is it
uh
n?
yes, yeah. That follow because of C. Suppose two okay, two ways to do that. If suppose two numbers are not co-prime. Okay, so we will change colors like so many times. Yeah. So suppose we have some staircase and this number. Okay, this C and some this B. Now, if they are not co-prime, okay, so C is B plus some number A, correct? So that number could be here, like here, somewhere. And if like two numbers are not co-prime, that's supposed to mean suppose like this B and C are not co-prime. So P divides B, P divides C. So P also have to divide A. Okay, so B and A actually are not co-prime now. Now we will use minimum argument. Like suppose the minimum depth. So like beyond this pair of like A and B, there are no pair above which are actually co-prime to each other. But if you try to see, B is actually equal to A plus some E here, which can be like staircase or something. But then again we have like P divides E, which contradict to like minimality. Or yeah, and because we like from the start we never have sum of two co-prime numbers. If we have anytime we have sum of two co-prime number, that number and the like the previous number should be like if you have some a plus b equal to c, and suppose this a and b are like divided by p, then one of this a or b actually formed by a plus some e, and then we again have p divides e, and this will continue till back, and we cannot go like till back because like from start we have all like non-co-prime numbers sum. Or the better way to visual like understand what is going on. Suppose we have some number here n which is a plus b. Okay, so what does this mean? There's b here and a is somewhere here. A can be like there's no staircase at all or some large staircase. Now if you go here, that is n plus b, which is actually a plus b plus b. Or you go here, which like follow the staircase pattern again. So this will be n plus a. So this is a plus b plus a. Can you guys see some like this is not normal. So like if we have two numbers a comma b at one pair and that sum into n, the left and right thing are actually nice. They are actually a plus b and a plus b plus a. And you can observe it here. Like okay, we have this 5, then this is 5 plus 2. Now 5 equal to 2 plus 3. Now 7 equal to 5 plus 2, 5 plus 3. Now suppose we take this. So 7. Now 7 equal to 5 plus 2. Then 9 equal to 7 plus 2 and 7 plus 5. So this pattern actually follow. There's like definite pattern. So from like, okay, rather than denoting by n, we denote this vertex by a comma b. And we're considering sum of a plus b. Then actually from a comma b, we are going to either a plus b comma b or a plus b comma a. The like greater and smaller thing can consider later. But yeah, actually, yeah, this should be b comma a because b is greater than a in our thing. But yeah, this is how it's going. So have you seen this pattern somewhere? Like from a comma b, we go a plus b comma b. Or you can go like reverse thing. So from a comma b, we go to a comma b. Sorry, a plus b comma b to a comma b. Something.
Fibonacci, like
No, not
2D
Fibonacci.
Fibonacci.
GCD, no?
What?
Like GCD of A
Yes.
plus B come.
Yeah.
Oh, yeah.
This is Euclidean division lemma, guys. Have you remember? So like, if you have a plus b, the GCD is equal to like a minus b comma b. This is same thing. From a plus b comma b, we go into a comma b. So if you follow like, here we have 8 comma 5 here. Then we go to 5 comma 3. Then we go to 2 comma 3. Then we go to this is 2 plus 1. And then 1 comma 1. So GCD is 1 actually. So this is actually this tree called a pure like Euclidean tree because this is actually a Euclidean division. Isn't that so amazing? That's why I like this question. Yeah. Yes. So this is actually everything is just Euclidean lemma. So like from this 7 is come from like 5 plus 2, which is like subtraction of 5. So each pair actually rather than defining 7, we define like 5 comma 2. Now each pair can be like defined like this. So this is actually 7 comma 2 and 7 comma 5. This will be like some 5 comma 2, 2 comma 3. Yeah. Yeah, this is like a very nice question. So now what we have? So okay, now another way. What is actually for like phi of n thing? We go here. So suppose a plus b equal to n, right? If a is co-prime to n, then b also co-prime to n. Everyone agree? Right?
Yeah.
Yes. And if a is not co-prime to n, then b also not co-prime to n. Everyone agree on that also. Correct?
Yeah.
Yes. So if you consider any co-prime number to n, which is a, then b, which is n minus a, also co-prime, right? So all we need to find like the number of we say a number of phi of n is actually equal to pairs a comma b, such that a plus b equal to n. So phi of we have another not a definition, but like the conversion phi of n is equal to the number of pairs of a comma b such that a plus b equal to n. And what? Yeah, and a should co-prime to n. Or basically what I'm saying, a and b are co-prime. Because if they are not co-prime, then this will be not. Yeah. So number of pairs of a comma b which has GCD1 and sum equal to n is equal to phi of n. Everyone understand? Cool. I suppose yes. And so now what we have to find is like the number of ways n come in this tree is actually equal to number of way we write a comma b equal to n. Right? And so, and we know like this, all of the pairs at vertex are co-prime to each other. So actually the anytime n come, it is a sum of two co-prime numbers. So we just have to find each pair of co-prime number come. But this is actually the Euclidean tree. So like from 1 comma 1, you can go to any pair, right? Like add 1 or add 2 or add 1, add 2. And this, because of Euclidean lemma, we always get every pair exactly once. Because Euclidean lemma follow in one dimension, like only one way. Remember, like that's why Euclid is so famous, like division lemma, because there's only one way to go from this thing to like GCD. So like what are we actually saying in this by like Euclidean tree? There will be every pair A comma B, such that they are co-prime to each other, and the sum is n. And so there are total number of n comes are like actually phi of n. So that's why the total numbers of worm is phi of n. Did you guys got the like how we go? Like first we try some small cases, then we try like okay, during the addition, what is staircase? Yeah, that's a good question. So actually, no, so the intuition is like, what are we actually doing? We either place horizontal block once, okay, uh, here. We either place like what is it? Horizontal block, which go to like previous case, or we place vertical block. And when we place vertical, if it's like near to the staircase will follow till the staircase end, right? Now, what are we doing here also? Same thing. So if you are going like only same side as previous, we actually adding these both things. And if you going like left side, then this is like some staircase in tree also. And that's why we just follow till here and add one. So here, suppose you consider this number. So staircase go like this. So in like one thing, this point, okay, this point we denoted by this. So one, left, right, left, right, left, up. Yeah, this one is denoted at this vertex. And if you consider this vertex, this will be something like this. And rather than going up, we go only right. No, why? Yeah, this is at this vertex. Everyone understand? So each of the branches go to either left or sorry, right or up, and the staircase pattern also follow in the branches. And because of the way the branch is created, we get every pair is actually co-prime to each other, because actually we go from like A comma B to A plus B comma B and A plus B comma A. If you define each vertex a pair actually like 3 comma 5, this is 5 comma 8 and so on. And because like initially everything is co-prime, so later also everything co-prime by the Euclidean division lemma. And because of this Euclidean division lemma, same thing, we get number of pairs is equal to phi of n. And because of like again Euclidean division lemma, number of pairs, this tree will have all the pairs. So everyone understand and how this problem actually like process. Yes.
Oh, wait, I missed the last part.
Okay.
The last notation is wrote. I missed that. So.
Okay, yeah. So this, okay, wait, just a second. Why am I doing this? Right? Anyway, the notation, this phi of n denote the number of number less than n co-prime to n.
Oh, right.
Yes. So like, oh,
Makes
here I explain. So like the number of number, like suppose phi of 10. So how many numbers co-prime to 10 actually? The like, there are so many, like what? 4. There are actually 4. So like one, not 4. Wait, I'm mistaken. 4, 5. There are actually 4 only, 7 and 9. Co-prime. Okay. And so, and this is same as this. So suppose A comma B pair co-prime and sum equal to n, then this is co-prime to n. So like all, consider all the co-prime numbers and it relatively B, which is also co-prime to A, and that's why this is phi of n. And this tree always cover all pairs because of Euclidean division.
Right. Okay.
Yes. So do you guys understand? So the first part of the problem is understand the process, like what is going on. And because like we have some kind of intuition, we going for Z, we define the recurrency like nice visualized way. And once you got this tree, then it's just observation that yeah, you lemma and so on. Everyone understand, and everyone like
Yes, sir. What's the source of this problem?
yeah, everyone understands the like beauty of this problem.
Yes.
The
So
source?
okay. Source is the TOT, like Tournaments of Town 2019, senior, I guess P7 or something, like senior's last question. I will share in like, okay, I don't have it open. I have to search now. Yeah, the Tournaments of Towns are some like very nice question. Yeah, but I hope everyone understand it. Now everyone also understand over the
But what gave
lecture
you the
thing.
idea to like turn the tree around, like to make it a tree like that, binary tree?
Okay, so this recurrence idea is come from like first you try for like Fibonacci, which is like recurrence. Then you come up with yeah, this is recurrence. Then one of the observation is to consider like okay, this is too much amount. Yeah, staircase. And once you observe staircase, this is the idea to come up with tree is like see each time you have two ways, right? Either you go down, and whenever 2 comes up, 2 is like either you consider any type of binary things. Here you can actually consider binary tree. And each problem has that thing, right? Something which is obvious, but it's come as some idea, visualized idea, which make that problem different. So this is the like part of the problem. You consider tree, and once you consider tree and the vertex as a like first you consider as a sum, then you understand you and then you understand yeah each thing follows very nicely. I hope and uh, what answer your
Yeah,
question.
yeah, I answer.
Yes. Yeah.
Yes,
Anyone have any
yeah,
doubt or
it is kind of
uh,
graph theory idea.
okay, so tree is like graph theory is like sometimes we use some theorems like theory, but this is not actually any theory, right? Like we don't use any type of tree thing here. Do we use? No. We just like this is just binary tree, like just way to visualize, right? So like there are many ways to visualize. If you like have some square and you go in here from here, then there's another some way of visualizing in graph theory terms. In graph terms, actually. So graph is like way of visualizing in substance. So this is like visualize. There's no graph theory things. Actually, I have one graph problem. No, we will not cover that. Okay, I pasted the thing, link for problem. I will also suggest to go over the okay. Actually, while writing the solution, so first of all, this question will not come for InMo, like definitely. I mean, they are not. I don't know what they like do if they put this in. But it's like TST or some IMO level question. So like sometimes they understand what are you saying. Sometimes you like you don't have to like total rigors. So here you have to like consider this Fibonacci like say this recurrence thing to prove this staircase is fixed, which you can prove like by saying like yeah this is like this horizontal cover is fixed, so we have to cover this and this in substance. And then you consider this binary tree and then you argument that this follows, which is actually Euclidean division lemma. The number of these such pairs are phi of n, and all of this pair come because of the Euclidean division lemma. Yes. Okay, everyone has. I like there are 10 people. Yes. Yeah. So I guess yeah, I hope you like today's session and like problems too. So the first one is just like sometimes you have to try larger cases and like try smaller cases which actually help. I also want to say like sometimes they did not also help. Like sometimes you just confuse the thing and you have to actually look at the overall problem. But that's the point. Like once you solve more problems, you come up with what should we do and like what should idea. Now once you the here was main thing was consider this construction, and once you come up with construction, this is like some argument to make it like bounded. Then this was a nice problem. I will suggest like the if you want to try like hard problem or 3D thing, also try 2017 C6. That it is also hard problem and also 3D like cube things, and you will have fun with this problem, a lot of fun. Okay, the in this problem we actually like consider each thing individually and like come up with construction, which is like nice if you have cube or something. I hope they don't allow Rubik cube in contest, but yeah. Then you have 6 by 6 thing. Like okay, you can actually do it for like 4 by 4 and just draw the question in the paper and draw this some kind of argument in construction or this face wall argument. Both works, I hope. Like yeah, once you like write everything proper, like makes sense, then you get the points. For like hard questions, this is the time like they don't actually like say like you cannot explain this, you have to explain like this and some coordinate system and like every point. You can just mention it. And I will suggest to everyone look at the EOPS post and solutions. Yeah, I mentioned the source USMO 2022. Yeah, and then you come up with an argument to say this is 2, 3 and by 2. This you can say by intuition. Like by intuition, we have each thing should have upper thing and something like that. And now you just have to concentrate on like the orientation, like the 3 orientation, and that's then it's become just argument. Yes. Okay. I think this bubble problem is also nice. Yeah, this is also a nice thing. It's not combi like combi thing, like not some visualize, but you can try. This I don't know. I'll put it in this. We have this problem, which was like huge and like nice. Okay. I hope everyone liked today's session. Anyone have any doubt like about anything? Feel free to speak up. It's already, yeah, already.
Uh, can you send the AOPS link? I can't use AOPS really well. Of the
AOPS link. Okay, I will
USMO
send
problem.
on like a USM problem. Okay. Actually, I have 3 links on like Discord at common. What is that? The general, in general, I will send it. I guess, yeah, I don't have the AOPS open for that. Anyone have any other doubt, please? Okay. Yeah, I found USMO 2020. Yeah. Any other doubt regarding that? Yeah. But yeah, I hope you enjoy the lecture. So like the main part was like example, get the feel of the problem, what problem actually telling you, and try to like think on the like that process, how problem going. Some problem like fix the thing, like yeah, we have this thing only, and then you have to prove some bound. Or some problem is like nice, like previous, which we have to construct some nice thing. Yeah. So I hope everyone likes.
So wait, to get this intuition, we have to like spend time on the problem. That's it.
Yes. Yeah. So like, see, this problem was like some P3, P6 level. So like you have to spend so much time. So when I was trying the problem, I actually like try for like this case, some like linear case, then some staircase or something like that. And then we come up with this idea, like either you consider first part, this one, or you consider the staircase left part. And then like then the someone just taught me this problem like in lecture, and that time he like explained the like binary tree idea. So like actually Atul taught me this question like in some lecture, and so this binary tree idea just come up. Like this is like main one of the point of the question, like why question is unique, that this one. And this tree is actually very nice because it's just follow the Euclidean division. And this is also hard to notice. Okay, so like we obviously we write sums, we don't write the pairs. You somehow have to come up with the like thing, like we actually come up with the pairs, and then if understand, yeah, this is about the sum of the number, then you come up with it's just Euclidean. Okay, yeah. I guess I will stop the recording first. Okay. Bye.